Log on, tune in, find out. Another good idea from Cambridge.
Organiser of the workshop, Stan Zachary, who's going to speak.
Okay, so thank you very much. I shortened the title from storage and demand shifting to buffering. And one of the points I'd like to make is that these both storage and demand shifting are aspects of the same thing. The other word in the title is taxonomy, and the motivation for this is really, there's been a lot of work in the past in mathematics in the last 30, 40 years, ongoing work in probability theory stochastic processes applied to communications networks. And if you spend some time in that particular area, you begin to realize that there are various different types of models people talk about. They talk about the simplest model. In the old days it was circuit switch networks, so-called the Erlang model, and then they talk about things like models with control in them, and then they talk about models with large deviations results, and they talk about models in networks and how these work. Are they controlled? Are they uncontrolled? They talk about models in which different traffic streams have different priority levels, and models in which different traffic streams have different levels of flexibility as to whether they can be postponed or not. In the internet in particular, that's a question where you would distinguish between streaming video traffic that cannot readily be interrupted, or between transferring large files. It doesn't really matter if they're held up for a few minutes. And if we begin to understand how we use mathematics in managing uncertainty in energy networks, there are going to be a whole lot of similar issues. There are going to be a whole lot of similar models, and we need to begin to try and understand what those issues are, what those models are. And this is just part of the, it seems very abstract to engineers perhaps, but it's just part of the way that mathematicians like to begin to understand what's going on, and then what it brings at the end of the day that's useful frequently is not so much numerical results, but insights into how to control systems so that they work in a reliable and robust fashion, for example, and are reasonably resistant to variations in your assumptions. That's the robustness bit. So I just want to start the business of thinking along those lines, and it's going to be very simple, and to mathematicians it's reasonably well known, but it's just to sort of try and get some communality of how we think about these things. So the motivation, of course, is the fact that one needs to balance supply and demand. Is it minute by minute? Is it second by second? It's not quite clear, but to a first approximation, we have got inputs of supply and we've got outputs of demand. We have to keep them as close together as possible. Demand is not too difficult. Demand is variable, of course, but with people like Andrew Richards around, we can predict it pretty accurately to within less than 1%, and it's not too difficult to manage. We can schedule. It's not too difficult to schedule, for example, generation to match demand if we can control the generation. So demand is not too much of a problem. Renewable resources are the big new unknown in energy systems, the wind in particular. It's not so much that they're variable. It's a point I'd like to hammer home. If they were variable, it really, as came up in discussion with David Lenihan this morning, if we knew what they were going to do, if we knew what the wind was going to do, we could manage it fairly comfortably. The problem is that renewables are unpredictable. It's the uncertainty, not knowing what's going to happen, that causes the main problems. Okay. Examples of solutions. Well, better forecasting, of course, is a solution, but the thing I want to talk about a little bit about here is buffering. Storage is one form of buffering. You've got a bit of excess energy now, so you put it in a store and you use it later when there's a shortage. That's a bit like putting savings in your bank account. We know that, and people think of storage like that. Demand management. Well, if you postpone demand, it's like writing an IOU saying, well, please switch off your fridge or your heating system, different orders of magnitude there, please switch off now and switch on in half an hour's time when the load in the system is less. And so that if those fridges are allowed to warm up or the house is allowed to cool down or whatever, the energy is required a little bit later, and you have to come up with some extra generation at that stage. So it's a bit like incurring a debt. Write an IOU, and you have to pay it back. Maybe you have to pay it back. You might pay for demand to go away, but that's another matter. So it's also a form of buffering. It's like having negative storage from a mathematical point of view. You might at the same having positive storage is like having money in your savings accounts. Negative storage is like having a mortgage. You maybe have a whole lot of different accounts, and there are different types of flexibility, and you need some, and there are possibilities of environment between them. You can use some of your storage so as not to have to postpone demand, for example. Is it a good idea? Maybe it's not obvious it is a good idea, because you might need that storage because it's got very rapid response, perhaps, for some emergency in the near future. Okay, so there are issues there, but they are both aspects of buffering. Most basic mathematical model now in communications networks, we have very simple models, a single link model with inputs and performance characteristics. Basic mathematical model here perhaps is that we have an input which is generation gt at time t. Think of this, I'm thinking of this as a non-cumulative function of time. So gt is the generation at time t. Possibly you can control it. dt is the demand at time t. What we have to do is try and keep these two things, if they were completely balanced, if gt is equal to dt, there would be no problem. So what we've got are the imbalances between them, and to help us manage those imbalances, we have got a store of some sort. Let's suppose it's got a capacity B, but in practice, a very relevant feature of stores in energy networks, the practical people here will confirm, is the limitations on how fast you can put energy into them and take energy out of them. So we might, just to keep life simple, suppose there's an input rate equal to the output rate, which would be C. So the units of what's in the store, units of energy, megawatt hours perhaps, and the units of C are those of a rate, power. Okay, and we suppose that we'll just use ST to denote the amount in our store or buffer at time t. So clearly there is, we can write down, let's just for the moment keep life simple, takes the input rate to be the constraints and the input and the output rate to be infinite. Clearly when the generation exceeds the demand, you can put stuff in, your store fills up at this rate. Alpha might be an efficiency factor. You say that perhaps your store, you can't get out as much as you put in. We can just model that by saying we'll throw away a fraction 1 minus alpha as we put it in, if necessary adjust the size of the store, and when the generation is less than the demand, of course you would see something like this. And what happens, of course, is that if the store is full and you've got excess energy, you just spill that, and that's a loss to the system in this model. And if the store is completely empty, then you can't take any more out of it, so that is a case of demand that is going to go unsatisfied, and that's also a loss to the system. And if you want a performance measure for the store, you could use either of those, and in a certain sense that I'll explain in a minute, they can be regarded as the same. I'll come back to that. Okay. What about the value of buffer size? That's the first obvious question to ask. Let's have a buffer of size B, and let's increase its size by some small quantity dB. You just use a coupling argument, which you just think of increasing the buffer size a little bit. On each complete cycle of the store between being empty and full, you can count the frequency of cycling. A cycle means empty back to empty, having been full at least once in between, or equivalently, in the long term, full back to full having been empty at least once in between. Then in each complete cycle, you are going to, if you increase the buffer size by dB, there'll be a reduction in your spilt energy of dB per complete cycle, coupling argument, and there will be a reduction in on-met demand of dB. So in one sense, you can take the measure at either the upper boundary or the lower boundary if you're looking at the effect of increasing, at least if you're looking at the effect of increasing the size of the store a little. So the value of buffer size, if you put some value V on it, you've got this simple relation that dV by dB is the frequency of cycling and the level of the buffer is B. And if you go back to the picture and think about it, you imagine varying B. The closer B is to 0, the more rapidly you are having cycling between empty and full. So we can go back to here and say that dV by dB is a monotone decreasing function of B. And the moral of that is that a little buffering is very useful, and a lot of buffering in terms of adding a little bit more still is not so useful. The value of buffering is a monotonic decreasing function. The value of increasing the size of buffer is a monotonic decreasing function of the buffer itself. That, of course, is intuitively obvious, but it's nice to make it moderately precise, because what it does do is that, regardless of our control strategy, we've got a reasonably consistent way, I think, of measuring the value of buffer size. Okay. Okay, I haven't mentioned anything stochastic so far. We need to introduce some probability models. What just happens now in the simplest possible model, which is called the single buffer model, is that we allow our generation and our demand to be stochastic processes. GT is possibly controllable. That allows us to ask well-defined probabilistic questions like what is the value of buffer size? If we, this might be per unit time once the thing had settled down to equilibrium. Okay. Okay. So, and then once you start to ask questions about control, there's a whole range of different mathematical techniques that you might bring to bear. Again, very analogous to that which is used with communications networks. Now, I forgot to say at the beginning that all of this thinking is really joint work with my colleague James Cruz, Harriet Watt, who is unable to be here because he's got teaching commitments, and therefore, having said that, I can admit to having shamelessly stolen various of his slides, of which this is one. One interest of his is large deviations theory. One possible control, very naive in a certain sense, is that we have got a buffer of a certain size and we've got some stochastic process of demand, and so we will set our generation at some fixed level, which is just a little in excess of the average demand. So let's set the generation to be the expected demand plus fixed amount. Let's assume that the demand itself, or the stochastic part of the system, is a Gaussian process. The question that we might reasonably wish to ask here, and it is essentially the same as that of the value of the buffer, is if we wish to control the failure probability, the probability that we are unable to meet demand, the loss of load, just the loss of load probability that power systems engineers talk about. If we wish to keep that very small, which we typically do, and our buffer size is moderately large, then large deviations theory is natural here. We can so we can use a large buffer asymptotic to analyze this. Don't wish to go through the large deviations theory itself. One either knows about it, in which case I don't need to speak about it, or you don't know about it, in which case I'm not in a position to speak about it in the time available. But what a nice calculation, just a little more than the back of an envelope, says that what goes on here is that the larger the buffer size, larger the store size, the less do you need in terms of excess generation to control the probability, the loss of load probability to a particular value. Well, that's obvious, that inverse relation, but it is, asymptotically, it is precisely this relationship here. Constant alpha is something that depends on the covariance structure of the demand process. Okay, so that's one type of very simple control. Just put in a little excess. Something a bit more dynamic is perhaps of more interest. Let's move to a different model. Again, a single buffer. And let's move to discrete time. And we'll consider, to keep life simple, a perfectly efficient buffer. We've got capacity B. We'll suppose again, for the moment, that we don't have constraints on the input and output rates. Well then, let us make some further assumptions. Let's suppose that at time t, which we'll take to be integer, I'll come back to this, the state of the system is described by the level in the buffer, st, and that you're able to choose the generation over the next time interval, and there's an expected demand over that time interval, which I will call d bar t, and there's an error in that expected demand, which is independent of d bar t. Then, in this very naive first take model, nevertheless tells you something, and I'm supposing that the spillage of the losses occur at the discrete time intervals rather than continuously over time. So it really is a discrete time model. It's straightforward to show. In fact, if you think about it, you can see that the optimal policy in terms of minimizing the cost of possible spillage over the next time instant. If you put in too much, you have a greater expected spillage. If you put in too little, you may have costs at future times. Minimizing the cost, the expected cost of your immediately incurred spillage plus the costs of your future control problem in dynamic programming, the optimal policy is simply to get as close as possible to some target S bar at time t plus 1. Now the reason for that is that if you didn't have constraints on the buffer size, you would have st at time t, you'd add in gt, you would lose dt, and then it is the size of this quantity that is subject to loss over the next time instant, and which also the size of this quantity that determines the state of the system at the next time instant. So the entire optimization problem is entirely a function of this. It doesn't matter under our assumptions what st is. It doesn't matter what this should be d bar t. I'm sorry, d bar t is what you want to do is to get this as close as possible to some optimal level, neither too high nor too low. There should be an overline on the d, I'm sorry. Very naive model, much more interesting and much less obvious is if you can schedule, if we perhaps make our time units smaller, and you can schedule generation several time units ahead. Perhaps at time 0 you schedule the generation for t time units ahead, and then at time 1 you can schedule further generation for t plus 1 time units ahead, and so on. Then the state of the system is no longer just described by the level of the buffer at time t. It's described by the level of the buffer at time t plus the vectors, the vector of the different amounts of already scheduled but not yet realized generation. Okay, so the mathematical problems get more interesting, and I think it's Glyn at Heriot-Watt who is looking at that under, thank you Glyn, is that right? Well, I'll leave it to you. Good luck. Okay. So there are these mathematical questions that formulate themselves, and to the engineer they look quite naive perhaps, but they do, once we get answers to them, they allow us to look at real systems and to talk about real systems and to have some feel for whether they're being managed in the right way. And that's been very much the very successful model with communications networks. But the role of mathematics in communications networks has not been maybe entirely appreciated, because whatever the mathematicians do, the engineers fling in another optical fiber and all the problems go away. And this is definitely not the case with energy systems, that you can do that. Okay, now we've some hierarchy of models. We might try and classify them by, for example, considering first single node models. We can take a single node as before, and this is another slide stolen from James. His diagrams are neater than mine. We can have a single node, and we can have perhaps two stores, and that's a natural model to consider. They might have different characteristics in terms of how fast you can put energy in and out. You might have a large capacity store with a low input-out rate, a smaller capacity store with a high input-output rate, and you might want to use these. The large store might be a conventional store. The small store might correspond to dynamic demand. We've already made the point that demand is just storage. Well, it's negative storage, it's buffering. Maybe just use the word buffer. We might have a small store that is much quicker to respond. It has a, because there's a much higher input-output rate. That might correspond to being able to switch people's fridges on and off, or more significantly, their heating systems on and off. But perhaps demand can only be postponed for short periods of time, and so you might have your small store might indeed model dynamic demand. It's a quick response, but relatively small size. It's natural to look at this type of model and to look at what, given that, and again given the same sort of loss function, is an optimal control strategy. And it's mathematically, to me at least, it's far from obvious. And it's one of those things that we'd like to do, because it will provide insights as to how we integrate storage on the one hand and demand management on the other. Okay, so that's one level up in our taxonomy. It says, let us have, we need to understand not just the single store, but we need to understand multiple stores and how they interact with each other. Okay, how do we go wider in the in this classification? Well, we can look at network models. That is the obvious and the interesting and the difficult problems. Again, parallels with communications networks. We looked at single, once upon a long time ago. We looked at single links, and then we looked at models and networks. Well, we have similar problems here. The simplest mathematically network model is to have two nodes, each with its own input and output, and each with its own store. So it's two of the models we looked at previously, and then to join them by a link which has got some capacity L. And of course, again, mathematicians like to look at extreme cases. If the link really isn't, if L is equal to 0, the link really isn't there, and the two systems become separate, so we already know how to handle that. If L is infinite, then these two nodes collapse into one, and we're back to the model we looked at a minute ago. But if L is finite, then there is a possibility to use either store to help buffer the imbalances in the other half of the system. And there's the question, so the question mathematically is, in terms of the cost of operating the system, how does that cost, which presumably goes down as L goes up, how, in more detail, does it behave as a function of the capacity of the link? And as before, there are all the control questions. If you've got excess energy at this node, should you put it into this store, or should you, while you have an opportunity, send it down the link to this store, which perhaps has considerably more spare capacity in it? Not at all obvious. And these relate in practice to modeling the effects of the transmission system, of course, because one of the problems one has to worry about in the case of intermittency, and in any case, is that individual generators, for example, might discover that they had local monopolies in space of energy supply over some period of time, because in some given region of the country, demand exceeded supply, or would exceed supply in the absence of that generator, and the network has got insufficient capacity to bring in supply from elsewhere. And so there's a local monopoly created that the generator can exploit to charge whatever price they like, pretty much. And if you have a possibility of moving energy from into the vulnerable region ahead of time, putting it in storage, then you can break that monopoly. So again, storage and buffering assist in managing the system, and they change the optimization problems that we would like to ask. But when we look at these sort of multiplayer optimization problems, where individual players are each trying to maximize their own profit, we change the dynamics and of those systems and the way they operate. So it's time for me to stop. I am, apart from some of these very elementary things, not producing mathematical solutions. We're saying that there's a nice hierarchy of problems, and we need to solve them. We need to talk a lot more to the practical people to see which ones are most relevant, but this type of thinking gradually begins to build up the insights which we hope will be helpful. Okay, I shall stop there. Phil, sorry.
Just a couple of comments, really, I guess, rather than questions. The first one was, you talk about demand and saying that demand is reasonably predictable. And I guess what you're maybe thinking about there is predicting demand on a national level, where you've got a large population. I guess some of the work we do on storage and demand management when we're in the distribution network, so we're looking at localized constraints or localized problems, the demand group that we're having to be able to predict is quite a lot smaller in terms of the number of customers, and therefore becomes harder to predict. So that presents something a little bit more challenging when you move down to the lower levels of sub-regions of network where there's a localized issue.
Smaller scale systems are always, relative to their size, more challenging, because you don't get those benefits of aggregation And certainly you don't get the demand internationally. I tend to view these things, just because who've been talking to so far, from the point of view of the control room in Wokingham. I shouldn't say it's in Wokingham, but wherever it is. Clearly marked on OpenStreetMap. In principle, it should. One's concerned with the imbalance between generation and demand, and what you have to predict primarily is what that imbalance is going to be, because that's what you need to buffer. So it's easy in the sense that what you're really saying is that on smaller scale systems there's more variability. The reason why I said put that up in that slide was just to say that when it comes to things like wind integration, I don't think that variability is the big problem. I think it's uncertainty.
Yeah.
That's the big problem. A lot of people say, wind farms, no use because the output is so variable. But if we know what it's doing, we can go a long way to managing it.
I guess I'm just saying, if you've got a smaller group of load customers, the uncertainty in future demands is greater as well. And so we see that as a bit of a maybe more a stronger challenge in a distributed
it is a stronger
context than where you are.
It is.
And then the other one I was just going to say is that I think there's an interesting piece in the link that you've got on that slide there, where you say L, the fact that the capacity of that link will also change with weather patterns and with wind speed and with ambient temperature, adds another really interesting, I think, angle to this work. And the fact that things like ambient temperature and weather patterns affect demand and affect wind power output, driving that link L, the capacity of that link. I think some work that looked at all of that together would be really very interesting. That is getting, even more challenging. I mean, we've done some work at Durham at looking at that capacity L and how it varies with weather patterns, so maybe that's something we can look at.
That we need to talk about.
I think it's quite interesting that that capacity is influenced by the same things that you're trying to deal with the uncertainty in already.
That's true. It's an extra layer of complexity.
Probably it's a very naive question, but I was kind of following on the point that you've made. Isn't demand dependent on the weather? So, I mean, where the weather is so we have extreme events there. When the weather is very cold, probably demand would go up. And wouldn't that, it's a naive question, I know, but I was just wondering. Because there's a lot of uncertainty there as well that could drive.
That's a very practical question that David probably knows the answer to better. I mean, obviously it is dependent on the weather, but on the operational timescales, I think, and David will correct me, on operational timescales of a few hours ahead, one knows the demand reasonably accurately, because at that stage how cold it's going to be, which is the primary thing, is probably fairly well known. The wind itself is very fickle. David, is that right?
Probably the best man to answer this question.
Yes. The demand depends very much on the weather, but if you know the weather now, the weather in a couple of hours' time has been forecast, and it's not going to be that much different from what it is now, that you can say to a reasonable degree of accuracy that you still know what it is. And it's down to this thing that it is variable, but it is
predictable.
it's not predictable, but it's very nearly predictable.
Am I right in thinking there's also a link to the transmission capacity that you'd actually have between, I don't know if it's just interconnectors between countries, but between nodes and things like that, that if you've got colder weather, that's cooling the lines more, and so you get more capacity for transferring across.
That was Phil's point, and that makes it adds a further level of complexity.
And ambient
I don't know how much
influences it, but I guess that's relatively easy to predict. But wind speed and wind direction are two extremely important factors in the rating, for example, of an overhead line.
It's wind speed that we use most.
Yeah, and so that's
Yeah.
that links you down straight back to your wind power prediction as well.
Adds an extra layer of
Yeah.
stochasticity to what's going on. David.
Quick question. You said that national demand is relatively predictable. In say 5 or 10 years' time, when we have more storage on our network, do you think it will still be predictable?
I think it might still be reasonably predictable under a given control strategy if we're using that storage to manage the system, and if we're using demand management to manage the system. You know, one hopes demand management will make things better. I think, I mean, just my hunch, but you're obviously in a much better position to say than me, is that the major source of uncertainty, apart from system failures, is likely to be the uncertainty of renewable inputs, and that's the thing one has to work with. That's my hunch, but Andrew might know better.
Well, one of the things that has worried me in the past is if we go to shifting demand through some sort of demand management, and that demand management is voluntary, so that customers have the right to decide whether or not they turn off their fridge, and there's a price that they would have to pay if they don't, but they may decide not to. That you can that way introduce more unpredictability into the system by having that type of smart meter demand management type issue.
You have to tie them into contracts. Maybe, I don't know. Right.
So this is related to that question, but I suppose if you think of your two stores, then one of them is something that looks like you would be controlling in real time, whether to put energy into or out of the store. But another looks like something that you might have well chosen its dynamics earlier on when you set up contracts or set up protocols for the use of demand management. So
it's stochastic in nature.
Well, they might well. I mean, it depends what. It looks unpredictable now from the point of view of we don't know quite what those things will look like, but it might well be that they'll be easy to predict an hour or two ahead. Once they're settled on, once the control mechanisms are settled on. I mean, for example, it was something which adapted according to a signal that might be the frequency or something, then that would produce certain dynamics which we could predict. If it was some other thing that we decided upon. But those sorts of pricing schemes and regulatory mechanisms take years to introduce, so I don't think in the short term there'd be much unpredictability about it, because it would have been planned over several years.
Yeah.
I think.
The unpredictability I'm thinking about comes from the fact that if customers have the power to decide whether or not they utilise the contract, and you don't know how they're going to behave, that adds an extra.
Yes, until you have any data, but once you have data, they have at the moment the power to turn things on or off, and yet the total demand is reasonably easy to predict. So similarly, in that kind of context, you might expect sensible contracts and sensible pricing schemes to cause customer behaviour which was sympathetic to the network rather than disruptive to the network. And given that you had done that, it might be relatively easy to predict outcomes. I don't mean we could do it now, but one feature of a good pricing scheme or a good smart metering scheme or a good regulatory environment would be that it would produce behaviour that was sympathetic to the network. But I mean, it just wouldn't be a real-time control scheme then, would it? It's quite likely to be something which is embedded in the.
Well, then that would, if it was sympathetic, it would have a smoothing effect and reduce the complexity of the real-time control that was necessary. I don't know, it'd be interesting to know of current demand management schemes how much customer choice there was. Someone told me, this is anecdotal, living in a farmhouse in a remote region in France, far too far away, well, a long way from the centres of consumption, but had a very much cheaper annual electricity bill for, and it giving the supplier the right to disconnect them for a maximum number of hours in the year, a very small number of hours,
Right.
at the discretion of the supplier, which was a great value to the supplier in managing extreme loads.
So I wonder, is there any experience yet, just to ask the people from National Grid, is there any experience yet from things like dynamic demand, this the business of fridges coming on or off according to the frequency? Is there any experience of the impact of that on the grid yet?
I think there is a scheme from a company called RL Tech, where what they've done is contracted with large commercial organisations like Sainsbury's, who own many fridges in their stores, and they can receive an instruction from National Grid and pass that on to all their participating companies to switch off their fridges for a certain period of time. And that's more used as a frequency control mechanism more than a sort of a load moving operation. So it's not really storage on the scale that we're talking about, but it's a step in that direction. But you mentioned dynamic demand. I think there was a scheme to make fridges frequency sensitive. I don't think that we've seen any evidence of demand reacting to frequency in that way. Maybe Andrew could
Not that I know of. I think what there is on such a small scale, it's like a feasibility study rather than a feasibility study for which we have no data that I know of at the moment.
Coming back to my question, the worry that I have is that when we get into a world where we've got multiple gigawatts worth of storage on our network, they may be owned and operated not by National Grid but by independent generating companies who are motivated by their profits rather than by the security of the system. So maybe it's a Orwellian future I'm painting here, but this is something that we need to consider if we're
That's a third major theme. I said just at the beginning this morning, better prediction, buffering. But how to make the markets work in sympathy also with the system, rather than allowing people to create further monopolies. That's obviously going to be extremely important. I think generally there's a way people think about these, and Frank may want to comment, is to try to get a system that works well if people were playing nicely, and then to devise the incentives necessary to make them play nicely, given that they are naturally profit optimizers.
Sometimes economists think of that as the agency question.
Yeah.
Are you adding more agency? Participants? Perhaps one last question, then we'll move on.
I just had a quick question about the large deviations results you had, where your large deviations exponent depended on buffer size, which made perfect sense, and alpha, which was related to correlation of the demands.
Yes.
I wonder why it didn't relate to the correlation, a correlation to do with the generation as well. Were we supposing the
Well, this was a very simple policy in which the only thing stochastic was the stochastic process of demand,
right, okay.
and you just set the level of generation.
So it wasn't a
So
it wasn't a windy situation.
No, it's not a windy situation.
Right,
Okay.
Right, okay, thank you very much.